In this video, we will discuss one example of inductive proof. In previous video, we have already learned that there are two reasoning process, inductive reasoning and deductive reasoning. In inductive reasoning, we are moving from specific case to generalized rule. And in deductive reasoning, we are doing exactly reverse. We are already given the theory and we are trying to prove the specific case. For our further discussions, we will evaluate some of the mathematical simplifications that will help to simplify our computation. Sigma I is equal to 1 to n 1. That means we are adding 1 n times. So that will lead to answer n. I is equal to 1 to n 2. So summation of 2 n times would be 2n. Sigma I is equal to 1 to n I. So that will be summation over 1 plus 2 plus 3 up to n. And in mathematical formula, we can write it as a n plus 1 by 2. I is equal to 1 sigma I is equal to 1 to n I square. That would be 1 plus 4 plus 9 up to n square. And that we can simplify using the equation n plus 1 to n plus 1 divided by 6. Sigma I is equal to 1 to n. I cube is summation of cube of all the numbers, that is 1 plus 8 plus 27 up to n cube, and it simplifies to n square into n plus 1 whole square divided by 4. Pi represents multiplication. Sigma is for summation, pi is for the multiplication. So pi I is equal to 1 to n of I is equal to multiplication of all the numbers up to n, that is 1 into 2 into 3 into n. It is nothing but it's a simply factorial of n. So inductive proof, we have already seen one example in previous video. We will try to prove that using the mathematical induction. So to prove the P of n, that is P of n is any generalized observation, we need two things. One is a basis case. So we will prove it for the smallest value of n. That is, we need to prove that P of 1 is true for initial value of n. Some boundary condition would be given that at least for this n, this given statement is having this value. So that we need to prove for the smallest possible value. And then we will assume that our hypothesis or our assumption is true for some value of k. Okay? So we will assume that P of k is true. This is our assumption. And based on that assumption, we will try to prove that the given statement is true for k plus 1 as well. So if we can prove it, then we can say that our statement is generalized and it can be proved for any value of n. So these are the steps for mathematical induction. Consider the example. If x is greater than or equal to 4, then 2 power x is greater than or equal to x square. This example we have already solved in previous video, but here we will try to solve it using the mathematical induction principle. Here, the base condition is already given that conclusion is true for value of x greater than or equal to 4. So 4 is the starting point. That is the initial value. So we need to test that whether our conclusion is true for x is equal to 4 or not. So if we replace x is equal to 4 in conclusion, it would be 2 power 4 greater than or equal to 4 power 2. That is 16 greater than or equal to 16. That's obviously true. So we can say that P of 1 is true. That is, for boundary condition, the given statement is true. Let us assume that it is true for x is equal to k as well. So we can say that 2 power k is greater than or equal to k square, because we have assumed that it is true for n is equal to k as well. We have to try, now we have to prove it that it is true for x is equal to k plus 1 as well. So in our original conclusion, we will replace x by k plus 1. So that would be 2 power k plus 1 greater than or equal to k plus 1 square. This we need to prove. So let us rewrite it. 2 power k plus 1, we can always write it as a 2 into 2 power k. And we already know that 2 power k is greater than or equal to k square from equation 1. So 2 into 2 power k would be definitely greater than or equal to 2 into k square. Right? We are just utilizing equation 1 into this. On right hand side, we have a k plus 1 whole square. Right? So we have to prove that 2 into k square, which should be greater than or equal to k plus 1 whole square. Then we can say that the statement is true for n is equal to k plus 1 also. So let us simplify it. So 2 into 2 k square is greater than or equal to k square plus 2k plus 1. Then k square is greater than or equal to 2k plus 1. K square has been removed from both the side. And then we can say that k is greater than or equal to 2 plus 1 by k. On both the sides we have divided by k. If k is greater than or equal to 2 plus 1 by k, then we can say that, okay, our claim is true. So let us test it for different values of k. Put k is equal to 4 into this equation. So when we put it 4, then the equation 2 would result into 4 greater than or equal to 2 plus 1 by 4. That is 4 is greater than or equal to 2.25. So it's true for k is equal to 4. If we put k is equal to 5, then equation 2 would be 5 greater than or equal to 2 plus 1 by 5. So that will be 5 greater than or equal to 2.2. For 6, it would be 6 greater than or equal to 1.667. If we observe this pattern, then on left hand side it is increased by 1, 4, 5, 6, 7. And on right hand side value it is decreasing. 2.25 was initially, then it became 2.2, then it became 1.667. So on left hand side it is increasing, on right hand side it is decreasing. So this inequality will be always hold for any value greater than or equal to 4. This inequality is going to be true forever. And that is why we can say that 2k square is greater than or equal to k plus 1 whole square. That we have proved through this steps. And hence it is proved that 2 power k plus 1 is also greater than or equal to k plus 1 whole square. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.